Hello, this is an explanation of the Huffman tree. The Huffman tree is the binary tree structure used in Huffman coding, which is the algorithm used for compressing and decompressing data by assigning variable length codes to characters based on probabilities and frequencies. The goal here is to minimize the overall length of the encoded data, and on the tree, the left node is assigned with 0 while the right is assigned with 1. Now let's take a look at an example. Here, the probabilities are assigned to 5 different characters, E being 0.4, T being 0.3, A, I, and N being 0.1. These probabilities represent the frequencies of each characters and data to be compressed. Now, the code words are assigned to each character based on their probabilities and their place in the Huffman tree. We'll take a look at a visualization site that shows this part in more detail later on. Characters with the higher probabilities have shorter codes. Now, the average bit per character using the Huffman code is calculated by the probability into the length of the code. Now, in this example, the average is about 1.7 bits per character. Assuming that a fixed length encoding of 3 bits per character, to find the compression ratio of this example, we do the following. 3 minus 1.7 over 3, all of that into 100, giving us 43.33%. Now, this means that the Huffman coding achieves a 43.33% compression ratio compared to the fixed length coding. This is a visualization of how the Huffman coding works. As you can see here, the lower nodes are joined together until the entire tree is created. As you can see here, the E is given 1, because as we said, 0 is on the right side and 0 is on the left side and 1 is on the right side. E is 1, T is 0, 1, A is 0, 0, I is 0, 0, 1, 0, N is 0, 0, 0, 0, 1, 1. Now this Huffman tree uses the greedy strategy, which makes locally optimal choices at each step to achieve an optimal solution. This is done by merging the 2 nodes with the lowest frequencies at each step of building the Huffman tree. Now we move on to the algorithm itself. Here in this code, the Huffman tree is explained. Now first, the mini heap represents a node in the tree. This node contains the character and its frequencies, the amount of time it appeared basically, while also initializing the right and the left nodes with null. The tree is constructed by repeatedly extracting the 2 nodes with the lowest frequencies, combining them into one node. The print codes function recursively traverses the tree starting from the root all the way to the last node in the tree. And the main function then calls the Huffman code function with an example to show how the algorithm operates. This is an implementation code of the Huffman tree. We can play this so that we can see how this code works. As you can see here, this is an example. The array given is A, B, C, D, E, and F, with their frequencies varying from 5, 9, 12, 13, 16, and 45. Now, if we run the code, this is exactly how the first algorithm example showed. Each character with their respective codes. Now that we've seen an implementation and the algorithm itself, let's take a look at the analysis. The one here is for the base case of the problem. However, it won't matter as much since it doesn't significantly impact the rate of growth for larger inputs. Now the summation here means that for each integer from 1 to n minus 1, we calculate 2 log I. The 2 log is related to building the Huffman tree, where we remove the 2 nodes and insert in its place the node with the total of both nodes for each iteration until the tree is complete. This will then give us a big O n log n. Now before we wrap up, let's talk about space and time complexity. The space of this algorithm takes n, O of n, and the time complexity takes O n log n. This is because the number of iterations is proportional to the number of elements in the list, and the tree takes O of n time to display the nodes given overall in the algorithm itself. So the time complexity of the algorithm is big O n log n.